All right, and welcome back, everybody. So we just went through our quick review of eigenvalues and eigenvectors, along with some major results that you should be familiar with. And the next section is going to be a couple of results that you may or may not have seen in first semester. So we're going to go over these results with proof for a good portion, just so we can convince you that these results should hold. So this is going to be not necessarily review, but kind of a continuation of the important features of eigenvalues and eigenvectors that we need in order to move on to our singular value decomposition for compression algorithms. So let's go ahead and begin with the first of these results. And it's a lemma. This is kind of a step up into a major theorem. But the idea behind this lemma is that we want to show that eigenvectors are linearly independent in certain cases. So what I'd like to show you, what I'd like to begin with, is kind of give you a different kind of proof technique if you haven't seen it before. But I think the easiest way to show this result is through induction. So specifically, we need to show that eigenvectors that are associated with distinct eigenvalues are linearly independent. So what happens if our collection has but one object in it? Well, since eigenvectors are non-zero, we have a collection of one vector, and that one vector cannot be dependent. So this is a linearly independent set in the case where k equals 1. So this is what we call our base case, right? So we're the base step. And this is effectively the first domino in a series, right? We are trying to set up a whole bunch of dominoes such that when we knock over the first domino, all of the other dominoes will fall in time. So the base case here is showing that if k is equal to 1, right, the base case being we're inducting on the number of vectors in the set, because that eigenvector is a non-trivial or non-zero vector, then the set must be independent, and we satisfy this lemma in that case. So what we have to do now is set up our dominoes. We need to make sure that the k minus, if the k minus first domino falls, it is definitely going to hit the k domino, right? And we can follow that all the way back. K minus 2. And do. Yes, the sound effects do help. All the way back down to our base case. So if we knock over the first domino, then we eventually get to that kth domino, right? We eventually get to that kth step because we have established pairwise that these two guys are going to be satisfied, that these two guys knock each other over, and so on. So we are going to set up all of our dominoes in a row in what's called the inductive step. So that's what the remaining argument is, the inductive step. Okay? So in the inductive step, we get to assume that the k minus first domino is knocked over, or that it's falling over. What we need to show is that because this domino is falling over, the next domino in the sequence will also fall over. So we need to show that because any set of eigenvectors or k minus 1 eigenvectors corresponding to distinct eigenvalues is a linearly independent set, that if we start off with a set of k vectors with the same property, that they correspond to distinct eigenvalues, that this set is going to be linearly independent as well. So suppose indeed that we're going to show that we're going to try to create the trivial linear combination, or we're going to create the zero combination for some scalars, and we're going to say right now this is in a an algebraically closed field. So C, the complex numbers, is a great place for this to hold up, because this result actually does work for complex eigenvalues and eigenvectors as well. So suppose that we have some zero linear combination. So we're going to try to show that all the CI scalars are zero, That'll show independence. Okay, so consider what happens when we hit this this star equation with the matrix A. Right, through linearity, this A moves through, it distributes to each member of the sum, and the scalars factor out of that multiplication as well. But notice that by definition of eigenvectors, or by the definition of an eigenvector, that A times Vi is the same thing as lambda I times Vi. That there is, instead of a matrix multiplication, or we can trade out the matrix multiplication for a scalar multiplication. So, multiplying this star equation now, if I go back to the zero combination equation, if I multiply this guy, instead of hitting that vector with a matrix multiplication, I'm going to multiply on both sides by some lambda j, some eigenvalue, which would mean that the zero combination is equal to A times this vector, which we already established comes down to this, right? That would be these two equations being the same, right? These guys are the same expression. But because I have the zero combination, I can go ahead and add or subtract any non-zero, any multiple of equation star. And that's exactly what I'm doing. This is effectively lambda j times the zero vector. I'm adding nothing, or I'm subtracting nothing from this guy, but I'm doing it in a very, very particular way. Because when I do this, notice that I cancel everything, or I cancel out exactly the lambda I and lambda, or there's a specific, oh shoot, what am I trying to say here? There is one guy here that is omitted from the sum. So the these two sums are going to cycle through. Let's do it for a simple example here. The first one, C1 lambda 1 V1 plus C2 lambda 2 V2 and C3 lambda 3 V3. If I subtract off of that, say lambda 2 times the original vector, then I wind up with C1 lambda 2 V1, C2 lambda 2 V2, and C3 lambda 2 V3. So instead of shifting the index on lambda j here, lambda j is actually fixed at a particular number. So I'm still going through each of the vectors V1, V2, V3, but I'm using just the same eigenvalue multiple on each of those, which means that these two inner, or the two vectors corresponding to lambda 2 cancel each other out in that difference. So I wind up with the following sum where I'm just omitting what happens on that middle term, or on that j equals 2 term. Hence why I have this notation saying that I get this difference between lambda j and lambda I on this particular vector. So that means that I now have a smaller collection of vectors. If I omit the j vector here, so specifically, if I get rid of that guy, which is exactly what I did here, this B prime is now a smaller subset, a smaller collection of vectors. And I should actually put that in right now, because that the way it's written right now technically is a mistake, so let me fix it. So kill off the comma. So we're going to skip over the jth vector because that guy was totally omitted in this linear combination in the previous line. This only goes from 1 to j minus 1 and from j plus 1 to k. We skipped over that vector. That means that this is now the expression that we would use, or an expression that we could use to create a zero combination for a smaller set of vectors. So this beta set now only has k minus 1 vectors in it. By our induction hypothesis, we get to assume that this beta prime set is linearly independent. Therefore, each of these CIs has to be 0. The last thing we would have to do here is show that, okay, well, all the CIs have to be 0, which means this CJ, the remaining guy that we originally took out, is the only thing that's left in that combination. And the only way that we're going to get the 0 vector out of this is if CJ itself was 0, because eigenvectors are non-trivial. Therefore, we have shown by induction that this set beta is linearly independent. So again, the statement of this lemma, if our eigenvectors come from different eigenspaces, then that set of vectors must be independent. Cool. So we're going to use this in the following theorem. Or, am I actually going to prove anything? Yeah, I'm just going to state a result. You are welcome. So, theorem. Let's say that I had a real square matrix with bases. Yeah, so if I have a basis for each of the eigenspaces, right? So this notation might be a little cumbersome, but think about it this way, that there is, for each eigenvalue of a linear subspace, right? There is an eigenspace, which is the kernel of A minus lambda I, for each of the eigenvectors. And each one of those vector spaces, I can assign a basis. And that's exactly what these guys are. These beta sub i's are just eigenvector bases for each of these eigenspaces. Then the set beta, which is the union of these guys, is going to be a basis for Rn. Right? So again, I have to be able to create bases for each of these eigenspaces. And that is only going to happen if my matrix is complete, right? If I can fill up the geometric multiplicity of each of my eigenvalues up to and include to fill up the entire algebraic multiplicity that I would get from the characteristic polynomial. So gluing all these guys together into one set, that's what this union notation is. Excuse me. That I'm creating one conglomerate basis, one amalgamated basis that is comprised of eigenvectors for my matrix. And so as a corollary, if I have a matrix that has n distinct eigenvalues, then I get this for free because the geometric multiplicity is always at least 1. And if I have n distinct eigenvalues in an n by n matrix, then my algebraic multiplicity at most can be 1. So that means the algebraic and geometric multiplicities are the same for each and every one of my eigenvalues. Therefore, I get an eigenvector basis for free when the matrix is complete. Or specifically, this guy is complete if I can guarantee n many distinct eigenvalues. Okay, so I've been talking theory for a while here. Let's show some practical examples of what I'm talking about. Excuse me. Sorry, I got a scratchy throat. So recall, we did this in the previous video or two. We already showed that this matrix A equals 4 by 1 by 1 by 4 has eigenvalues 5 and 3. So I can go ahead and construct eigenvectors 1, 1 and 1 by minus 1 for each of them respectively. So A represents a linear transformation from R2 to R2, and it's given in coordinates so it's given in standard coordinate bases as this matrix A. So we're going to go ahead and take B to be this matrix that puts V5, so an eigenvector associated with lambda equals 5 in the first column of B, and an eigenvector associated with 3 in the second column. So I'm going to fill up a matrix with eigenvectors of distinct of bases of the eigenspaces. And for this extra matrix, I'm going to create this matrix D. And D is going to just be a diagonal matrix. Clever name, right? D for diagonal. It's going to be a diagonal matrix whose entries are exactly the eigenvalues in the order that's presented in B. So notice I switched the order of 5 and 3 so you would pay attention to that. They're not listed in increasing order, they're just listed in some order, but I need to make sure that if the first column of B is associated with lambda equals 5, then the first entry of D must also be the eigenvalue associated with that guy. So in this case, it would be 5. So specifically, I can go ahead and represent this matrix operation, this choice of coordinates here. So the map that sends R2 to R2 via a matrix multiplication in A, if I were to change coordinates away from the standard coordinates to eigenvector coordinates, then the matrix representation of this linear transformation changes. And in fact, instead of being a full matrix, turns out D here is a change of coordinates, or that there is a change of coordinates transformation that makes this linear transformation look cleaner in a different basis, and specifically in an eigenvector basis of R2. So when we can do this, when we can write D, right, and the picture I like to give here, R2 to R2, this is what the matrix multiplication by A would look like. But I can change, and I think it would go this way actually. Yeah, I can use a change of coordinates matrix, and this would be B, right? I'm changing R2 into R2 through a change of coordinates matrix. But I'm doing it in in such a way that I can connect the two vector spaces with different coordinate descriptions via these matrices A and B. That going along the A side here is actually the same as going down, over, and back up. So down, over, and back up along that square. So we are effectively doing the same operation. We are still working with the same linear transformation, but we are skirting around using one particular set of coordinates in favor of the eigenvector coordinates. And when a matrix can be broken down in this way, where there is a diagonal matrix such that B times D times B inverse is a factorization where D is a diagonal matrix and B is a change of coordinates matrix, then we say that this matrix is diagonalizable. Okay, so A is diagonalizable if there exists an invertible matrix, right? This S is going to equal the change of coordinates from standard to maybe not necessarily from standard. No, totally, yeah. It's going to be from standard coordinates into eigenvector coordinates. And there must also exist a diagonal matrix D consisting of the eigenvalues of this matrix, such that, same idea with the picture, I'm going from bottom left, I shouldn't have erased it, A, R2, and then up here. Yeah, so S now is going to go in this direction, and D will go this way. So this circled equation is saying, instead of going right then up from the bottom left, we are going to go up and then over and wind up here. So we're just saying that these two expressions for that function are identical, and this is what's called a commutative diagram, or a commutative square. Very, very common visualization tool that we use in abstract math, and it does help to a large degree. But the point is, we say here that A is similar to D. And what that means is that these guys share eigenvalue and eigenvector properties. Or rather, specific, not eigenvector, they share eigenvalue properties. Right, so they share a characteristic polynomial, and they share, therefore, they share eigenvalues. So You may have seen the word similar before used in context, and that's exactly what we're doing here, showing why we care about complete matrices. And here's the next remark. Yeah, so specifically, if A is a complete matrix, then the matrices S and D are guaranteed to exist. And in fact, we can go ahead and say that these matrices actually satisfy the condition for A to be diagonalizable. So if you are complete, then you are diagonalizable. And if you are diagonalizable, then read off of the S matrix and the D matrix, your eigenvectors and eigenvalues respectively, so that you have full full eigenspaces, or you have full bases for your eigenspaces, or eigenvector bases of your eigenspaces. So that means that complete matrices are diagonalizable, and diagonal matrices are complete. Right? So just to show you what's going on here in this sense, just to kind of remember how diagonalizability works here, or how it doesn't work. Remember our Jordan block from before, right? This guy is not diagonalizable because the geometric multiplicity does not match the algebraic multiplicity of the eigenvalue 2. However, if I go to a larger system, right, so this guy is diagonalizable, and I can show you exactly how by exhibiting the matrices S and D. We should remember how to compute these guys just from what we had in the previous 2 videos. You construct these by filling them with eigenvalues and eigenvectors, which we just showed how to compute. So yes, 1 is repeated in this case, or 1 is repeated as an eigenvalue, but the geometric multiplicity of that guy is 2, and that matches the algebraic multiplicity. So lambda equals 1 is a complete eigenvalue. And since there is only the algebraic multiplicity of lambda equals 2 is 1, then we're guaranteed that this guy is complete. Therefore, the entire matrix is complete, and we actually construct a diagonalization of this guy. So this is the cleaner representation of the matrix of the linear transformation that is defined by that matrix multiplication A in the standard coordinates. So eigenvectors give us, in a sense, better coordinates, the natural directions, the natural coordinates that this matrix wants to use. We're going to use that to our advantage in practice. But let's go ahead and kill this video here, and I'll rejoin you for, let's see, what are we talking about in the next section? Yes, we are going for the spectral theorem. So again, a result that you may or may not have seen at this point, but nonetheless very important for us to show the existence